Hey again, guys. Welcome back. We've been talking about vectors, and we've primarily worked with what we call component form of vectors because it tells us the components, horizontal and vertical. We've added, subtracted, and multiplied by scalars with those forms. Now we're going to work with a form called magnitude and direction form. This basically just tells us the magnitude and the direction of a vector, so it's pretty applicable. A lot of times this is how we see vectors. So it's going to be useful to convert between magnitude and direction form and our component form. Thing is, this form is reminiscent of polar coordinates. So it's very, very similar, in fact, almost the same exact thing. It describes a vector by its magnitude, which is comparable to radial distance when we talk about polar coordinates, and direction, which is comparable to the angular distance that we saw in polar coordinates. So first thing, we want to be able to convert from component form, which we've seen, to magnitude direction form. So let's consider this vector r, where we have it in component form. Horizontal component is 3, vertical component is 7. And let's determine the magnitude and direction of this vector. Let's look at this visually. I'm going to sketch a coordinate plane, just focusing on the first quadrant because I know this vector should be in the first quadrant if I start at the origin. It's got a horizontal component of 3 and vertical component of 7, so it's reasonably somewhere up there. 3 is the horizontal component, 7 is the vertical component. Alright, so when we talk about it this way, we can really just refer to components as lengths. So the horizontal component we'll just consider as a magnitude, as just the length 3 right now. So it's just positive 3. And the vertical component we can just consider as positive 7. And what we're looking for here is the magnitude and direction. This is our vector r. It has a magnitude, which is its length, and its direction is the angle formed by the positive x-axis in our vector. So we start at the positive x-axis and go to the vector. That's the angle we'll call theta. So just like with polar coordinates, we want to figure out what those are. We know how to figure out the magnitude really easily. Magnitude is given by, we came up with this formula from the Pythagorean theorem. You can just do the Pythagorean theorem over and over again, but really, we'll just end up with the square root of the sum of the squares of both components. So 3 squared plus 7 squared. So the sum of the squares of both components. So the magnitude would then just be equal to, well, 3 squared is 9, 7 squared is 49. Add those together and you get a sum of 58. 58, well, can we simplify this radical? It's nice to simplify radicals if we can. So let's go to Desmos and try some things out. 58, well, we need to divide it by perfect squares. 58 divided by 4, no, that doesn't work. 58 divided by 16, no. 58 divided by 25, no. The next perfect square would be 36. Starting to see, no, 58 is not divisible by a perfect square. Therefore, this is not able to be simplified. So we have a magnitude of square root 58. You can approximate it as a decimal if you want, but I'll leave it as it is. Next, we need to figure out what the angle is. This angle should be really easy to find. We have the opposite and the adjacent sides of this triangle that was formed. Therefore, we can just use tangent. Tangent of our angle theta is equal to 7 over 3. Which means that theta would be equal to the inverse tangent after applying the inverse tangent to both sides of 7 over 3. Give that a quick shot in the calculator. Tangent inverse 7 over 3. I already have Desmos set to degree mode. You can switch between degree and radian. Is 66.8 degrees. Therefore, vector r in magnitude and direction form we'll write as, with parentheses to group it together, its magnitude first, square root 58, comma, its direction. So very similar to polar coordinates. This is the magnitude, comma, the direction. All right, with that in mind, it's not always going to be that simple as we've seen with polar coordinates, because quadrant 1 tends to be a little bit simpler, saves one step. So let's look at a couple that aren't in quadrant 1. Vector A, -2, 6 are the components. So if we were to start at the origin, that vector would be in quadrant 2. So I'll focus in on quadrant 2. Sketch our vector. Its horizontal component was -2 and its vertical component was 6. Again, what we want to know is what is the magnitude of this vector A, and also what is its direction. The direction starts here at the positive x-axis and goes to our vector. All right, so again we can form our right triangle out of this. And vertically it goes up 6, so it has a length of 6. And yes, it goes to the left too, but this length of that side of the triangle is +2. All lengths are positive. So we'll just use +2 instead of -2 when we're calculating this angle. Firstly, we can figure out our magnitude. Magnitude of this vector, again, is the square root of the sum of the squares of the components. So -4 squared plus -5 squared. Sorry, negatives. I'm looking at B. My bad. -2 squared plus 6 squared. Alright, a little bit of quick math again. -2 squared is 4. 6 squared is 40, so this is the square root of 40. Can this be simplified? Does a perfect square go into 40? Well, yes, it should be obvious that 4 is a perfect square and it goes into 40. So I can break square root 40 into square root of 4 times, well, the square root of 10. And this is helpful because, well, square root of 4 we know. It's a perfect square. It's 2. So the magnitude is the square root, or is 2 times the square root of 10. Alright, now we need to figure out theta, the direction. But using this angle might get a little complicated if we just go straight to finding it with that angle. So let's consider this smaller angle in here, alpha. We know all the way to this point, if we went all the way around, would be 180. So using that fact, we can figure out what theta is if we find alpha first. So tangent of that angle alpha would be equal to its opposite divided by its adjacent, so 6 over 2. Therefore, alpha would just be equal to tangent inverse of 6 over 2. Calculate that. Could just enter 3 if you wanted. Either way, you get 71.6 degrees approximately. It's not exactly what we wanted. We wanted theta. So to find theta, it will be equal to 180 degrees minus what we just found for alpha. Subtract those. 180 minus 71.6 will give us 108.4 degrees. And we now have alpha, or this angle, not angle, this vector A in terms of its magnitude and direction. So A is equal to 2 square root 10, comma, 108.4 degrees. Alright, I encourage you to pause the video and try the same thing out for that vector B right here. Keep in mind it's in quadrant 3. Alright, I did this one already. And having done the work, you should have found that its magnitude is square root 41 and its direction is 231.3 degrees. Big catch here. A common mistake people have been making with polar coordinates is still subtracting, but we know that it's in quadrant 3, so we go to 180 and then a little more, so we're adding to 180 degrees to find that angle. So it should be more than 180. Alright, so that's our process for converting from component form to magnitude and direction form. But what if we want to go the other way? We know magnitude and direction form, but we need to know the component. This is actually going to be a really useful tool if you ever take physics or engineering courses in college. So consider a vector P that has a magnitude of 5 and a direction of 37 degrees. Let's determine the components of P. So it doesn't really say what quadrant it's in, it's just some random vector. So I'll just say, well, the fact that it's 37 degrees tells us that it should be in quadrant 1. So let's draw our axis again in quadrant 1. And we know this time that the magnitude of this vector, P, is equal to 5. And they told us the direction is just 37 degrees. What we want to find, though, is what is the horizontal component. Turn this off. What is the horizontal component? V, or not V, P sub x. And the vertical component. P sub y. Right, in this case, we can still use right angle trigonometry. This is a right angle that's formed by the components. So we'll look at this angle, theta, which is 37 degrees, and to find this adjacent side, our trig ratio that will give us that is cosine, because this is the adjacent and we know the hypotenuse. And we know the angle. So right now what we have to find this horizontal component is the magnitude, or cosine, of our angle, 37 degrees, is equal to the adjacent, which we don't know, P sub x, over the magnitude, 5, because that's the hypotenuse of this triangle. Let's do this green. So we just set up this right angle trigonometry. We know that cosine is the adjacent over the hypotenuse. We knew the angle, we knew the hypotenuse. Now we can just solve to figure out that adjacent side. Multiply both sides by 5, and we'll get 5 cosine 37 degrees is equal to just p sub x. Use a calculator to figure that out. 5 cosine 37 degrees is 3.99. So 3.99 is equal to p sub x. So that's our horizontal component. And similar process for our vertical component. This time, the vertical component is opposite the angle. We know the hypotenuse, so we can use sine. Sine of that angle, which is 37 degrees, is equal to p sub y over 5. Same thing, multiply both sides by 5. So it'll be 5 sine of 37 degrees is equal to p sub y. Calculate that real quick. And it's 3.01. Notice those are really close to 4 and 5. Or 4 and 3, I should say, sorry. So there, we have our components. This vector p in component form is 3.99, comma, its vertical component is 3.01. All right, so in general, just to save ourselves time, let's look at a arbitrary vector. So let's let some vector v equal its components v sub x and v sub y. And we just want to consider, well, what will this look like in general if we just don't want to have to do any work over and over again when we're trying to get from magnitude and direction form to component form. So as a picture, this is just, doesn't really matter what quadrant it's in. I'll draw it in quadrant 1 again. This is our vector v. It has a vertical component, v sub y, and a horizontal component, v sub x. There's our angle, and this is our magnitude. Well, setting that up, we know that the vertical component, well, I'll start with the horizontal component. Horizontal component will just be the cosine of our angle equal to the adjacent over our hypotenuse. So cosine of theta is equal to the adjacent side, which was v sub x, over our hypotenuse, which was the magnitude of v. And we want to solve for the component. We would multiply by the magnitude on both sides. So to have the magnitude of v times cosine theta is equal to the horizontal component. I'll flip that around to make it look pretty. So here is how we can always find our horizontal component, by calculating the magnitude, or if we're given the magnitude, and then multiplying it by cosine of our angle. Same exact thing for our vertical component, except this time we're looking at opposite over hypotenuse, so we'll use sine. Sine of theta is equal to v sub y. over our magnitude of the vector v. Multiply both sides by v. And I'll flip it around. Therefore, we have our two components. And we can conclude that in general, if you want to find component form, when we're given magnitude and direction form, will always be equal to the horizontal component, which was magnitude of v times cosine theta, and the vertical component, which was magnitude v times sine theta. So whenever you need to find component form, you can just use these two facts, given the magnitude and the angle, or the direction. Alright, so looking back at our Angry Birds example, real-world examples are often similar to what we see here for Angry Birds. So I'm going to insert a quick picture of that again. Let's consider the initial velocity that this bird's launched at and its angle. So what we'll do is realize that this launch is a vector. We're calling this vector b. It's relative to an axis, a coordinate plane. We can pretend that there's some coordinate plane relative to its launch. And from there, we know it had an angle, a direction that it was launched at, relative to basically the ground. That angle was 34 degrees. And it was launched at a speed of 20 meters per second. Speed is a scalar value. So its speed is 20 meters per second initially. This is actually going to be the magnitude of that vector, 20 meters per second. And from there, we can just find our components. We now know in general that the components will be equal to the magnitude of b times cosine theta for our horizontal component, and the magnitude of b times sine theta for our vertical component. So let's quickly figure this out. I'll do them separately instead of writing them in here. This will be our horizontal component, b sub x, which will equal magnitude of b, which is 20, times cosine of the angle, which was 34 degrees. And the horizontal or vertical component will be equal to 20 sine of 34 degrees. And let's go to Desmos to calculate those. 20 cosine 34 degrees gives us 16.58, and 20 sine of 34 degrees gives us 11.18. I'll round those just to three significant figures, so 16.6 and 11.2. B sub x is equal to 16.6. B sub y is 11.2. So in component form, this vector is 16.6 and 11.2. So we know the vector horizontally and vertically of this angle, or of this launch. All right, next idea. We're going to be able to, or want to be able to add vectors when we're given them in direction or magnitude direction form. So if we know two vectors, how can we come up with their sum? Jonah, he's trying to do this. He's given two vectors, u and v. He says, this is easy. I can just add the magnitudes and add the directions together. So basically, he took the magnitude of u and the magnitude of v and added them, and the direction of both and added them. And came up with the new vector should just be 8, 165 degrees. Well, do we agree? Let's check it out. So again, we'll draw this. U is in quadrant 1, V is in quadrant 2. So vector V comes up to about here. It's 3, 40 degrees. This was 3. Or sorry, its magnitude was 3. And its direction, I'll do direction in orange. Its direction is 40 degrees. And B, or sorry, I keep saying the wrong things, W is 125 degrees for its angle and 5 for its magnitude. And this should say W right here. I'm not sure why I put V. And its angle goes all the way around. That's 125 degrees. So we want to figure out the components. The reason we want to figure out the components here is because we know how to add vectors when they're in component form from our last lesson. So if we can get these into component form, then we can add them and we can double check to see if we end up with the same thing Jonah did. Maybe this is a shortcut. So let's check it. Component form of u is what we need to find first here. So to find the components, we now know quickly how we can do that. The horizontal component would be the magnitude, which is 3, times cosine of, well, its angle is 40 degrees. And we can use Desmos to figure that out. Its vertical component, though, will be equal to the magnitude 3 times sine of 40 degrees. And we'll use Desmos to figure that out. So calculating it, we have, just going to use this, 3 cosine of 40 degrees and 3 sine of 40 degrees. That gives us 2.30 is how I'll round the first one, and 1.93. So 2.3 and 1.93. So in component form, u is equal to 2.30, 1.93. Encourage you to pause the video and try the same thing out for w. Try to figure out what the components of w are. All right, so if I do it, be w sub x, the horizontal component, is equal to magnitude 5 cosine of its angle 125 degrees. And w sub y is equal to 5 sine of 125 degrees. Quick calculations again, Desmos. We end up with negative 2.87 and 4.096. Negative 2.87. Yes, that negative matters. It's telling us the direction. This should go to the left, negative 2.87. And W sub y equals 4.096. So our component form of W, you should have found, was negative 2.87 and 4.096. All right, so what's really cool now is our third step in the process is we can add these to find component form of the sum. Of U plus W. So U plus W, we learned in the last lesson that when we're adding vectors, we just have to add the horizontal components and add the vertical components. So we're taking positive 2.30 and 1.93, adding that with negative 2.87 and 4.096. So like I just mentioned, all we need to do is take these two horizontal components, combine those, 2.30 plus negative 2.87, and our two vertical components, 1.93 plus 4.096. And from there, we should figure out the component form of this sum. Add these together, and we should get negative 0.57, 0.57. And when we add 1.93 and 4.096, I'll use a calculator. Is 6.026. So there is the component form of that sum. But we want our answer to be in magnitude direction form. So we'll take this, now that we know the components, and convert to magnitude direction form. So just to give us a visual, let's draw this in a coordinate plane. I know that that vector should actually end up in quadrant 2 because the horizontal component is negative, vertical component is positive. So the vector U plus W will end up somewhere over here. Vertical component is 6.026, and the horizontal component is negative 0.57. All right, so we need to figure out what is the magnitude of U plus W, and what is the direction. So what is this angle right here, theta? Magnitude should be easy as always. We're just going to take the square root of the sum of the squares, so negative 0.57 squared plus 6.026 squared. You can do that all in a calculator at once, actually. Square root of negative 0.57 squared. Make sure your negative's in parentheses. Plus 6.026 squared. Gives us 6.053. So there's our magnitude. Direction now. This is in quadrant 2, so we can figure out the angle alpha right here. This vertical side length here, didn't draw that straight, is 6.026. The horizontal side length is 0.57, just considering the positive length of it. So tangent of alpha is equal to the opposite, which is 6.026 over the adjacent 0.57. Use our calculator again to figure out what tangent inverse of 6.026 divided by 0.57 will be. Gives us 84.6 degrees. Got that from doing tangent inverse of 6.026 over 0.57. One more time was 84.6 degrees. Last step, and we're done. We know that this is in quadrant 2, so theta should be 180 degrees minus alpha. Minus 84.6 degrees. Therefore, theta is about 195.4 degrees. Did I do that right? 180 minus 84.6. It's 95.4 degrees. Whoa, where did I get 195? Just 95. Therefore, in magnitude direction form, U plus W, this will be where our answer is equal to 6.053, comma, 95.4 degrees. So with this in mind, was Jonah correct? He said it should be 8,165 degrees. Definitely not. So point of this is no, we can't, so in terms of Jonah, no, we can't just add magnitudes and add directions. We have to find the components. So this is why converting to component form is useful. We have to find the components, add the components together, and then convert back to magnitude direction form. All right, so hopefully this helps. You'll have an assignment with this as well. Have a good one.